And before we jump into this, let me just rewrite that formula again. So x plus some number a squared is x squared plus 2ax plus a squared. And since this is the intro exercise, we're really just figuring out what number we have to add to turn this into a perfect square. So let me rewrite what we have. We have x squared plus 18x. And we're not solving for anything. We're just trying to figure out the missing constant term so that we can turn this into a perfect square. So notice that the coefficient on x is this 2a. And the coefficient on x in our problem is 18. So 2a and 18 are the same. Or in other words, a is 9. And the number that we have to add, that missing constant term, that's a squared. So a squared in this case is 81. So if we rewrote this as x squared plus 18x plus 81, then we could factor this as a perfect square. This is really just now x plus 9 squared. And you can see that this is true because if you multiply it out, x plus 9 times x plus 9, you get x times x, which is x squared, x times 9, which is plus 9x. And now we distribute the 9. 9 times x is plus 9x, and 9 times 9 is plus 81, which is, after combining the 9x's, exactly what you started with. And you could also think about it from this left-hand side and factor it. So we know it's a product of two binomials. We know that since the coefficient on x squared is 1, this would have to be x and x, so we just have to figure out these missing numbers here. And we know they multiply to 81 and they add to 18. So the only two numbers that work for that would be plus 9 and plus 9. So either way you want to think about it, you can prove that this is in fact true. So the number, this missing constant term in the perfect square, is the 81. And let's move on to another one. And let me just make some more space. So we again need that missing constant term. So x squared plus 10x. And for all of these, we do want to have that formula. So x plus a squared is x squared plus 2ax plus a squared. Since we need the formula to match up what our a value would be, so that we can square it and add that to this expression so far. So just comparing, the coefficient on x is 2a, and here it's 10. So we have that 2a equals 10, or that a is 5. And so the number that we have to add is a squared, and squaring 5 gives you 25. So if you add 25 here, then you can change this into a perfect square, x plus 5 squared. And remember, once you figure out what a is, which is always going to be half the coefficient on x, that can immediately be put into this perfect squared expression. So in this case, the missing constant term that we had to add is 25. Let's keep going. We'll do a few more. So like I was mentioning above, the a value is always half this coefficient here. And you can use the formula to prove that to yourself, but a in this case would be -4, and the number we have to add is always a squared. So -4 times -4 would be positive 16. So if we were to add 16 here, we could change this into some binomial squared, or some perfect square. And again, the a value is always half that coefficient on x. So you would have x minus 4. And the sign is always attached to it. So if this is negative, then the a value on the inside would be negative. And again, prove this to yourself, remultiply it out, and show that you do get this quadratic trinomial. Or the other way to prove it to yourself is start with this trinomial and factor it. But in both cases, you'll see that this is true.